Hi, we would like to introduce our work, Content-Aware GAN Compression, a project collaborated by Princeton University and Adobe Research. Generative adversarial nets have received increasing focus from deep learning and computer vision community. It takes random noise as an input and generates a high-quality image which is fake but photorealistic. However, GANs are resource hungry. For example, GAN 2 is 250 times more computationally expensive than MobileNet v2, which is hard to deploy on mobile phones. Therefore, it would be necessary to develop a mechanism to compress large GAN into a small one. However, compressing state-of-the-art noise-to-image GAN is rarely studied, and using conventional methods yields poor results. We here propose an idea of content-aware compression. We look at the generated images from a GAN and extract their content of interest by image parsing networks. With the information of content of interest, we design a pipeline to compress large GAN into a smaller one, and name our technique content-aware compression. Our approach includes two components. The first one is content-aware pruning, achieved by a forward and backward path. We first forward noises to generate images, and then use a parsing network to find the content of interest. With the parsing, we add random noises like salt and pepper noise on the content of interest region to create a content-aware noisy image. We then construct a differentiable loss and backpropagate it into the channels. The channels that are sensitive to the content of interest are kept, while the others are pruned. To visually interpret the pruning strategy, we feed a random noise to a full-size model and obtain its output. We then feed the same noise to the prune models derived by multiple pruning metrics at different pruning levels. The images are like this. Compared to conventional weight or feature map-based norm-based pruning for the first three one, our content-aware pruning preserves the best information from the full-size GAN. In addition to pruning, we also introduce content-aware distillation. We feed the random noise to both full-size and prune generators. We then obtain the content of interest from the full-size generated image, which leads to two masked images. Then we insert the GAN loss on the generated image and impose distillation loss on the masked images. To interpret our distillation method, we look at the generated image and their content of interest from the full-size model, as well as compressed models trained by normal distillation and content-aware distillation. Visually speaking, our method achieves better distillation result, especially in the content of interest region. We conduct editing tasks with real images. Given two source images, we conduct style mixing with both the full-size model and our accelerated model. Our model better preserves the person's identity. For image modeling, we find our transition is smoother than the full-size one, for example, in the beard region. These results show our model could have a smoother and more disentangled latent space. We provide an extra example. Again, our model demonstrates a smoother transition, which indicates that it would have a smoother latent space. For quantitative measurement, we compare with a classification and a conditional GAN compression method. We find that our model achieves the lowest FID, which means its generative quality is the best, while we achieve the highest flops acceleration. We also measure the runtime speedup on V100 GPU. We find a 4 times speedup for image generation and a 3 times speedup for image projection on GAN 2. Please refer to our project page and archive link for more information about the paper. Thanks again for your attention.